All right, good afternoon and welcome to ECE 164 discussion section. A couple of announcements before we get going too much, and maybe the most informative way is if I post a poll. Oh no, this was gonna work. Maybe not. All right, sorry, I can't do the poll. For some reason it was working earlier and now it's not working. I guess that I'll just manually poll the class and ask you, how's the project going?
Slowly coming along. Slowly coming along.
Slowly coming along?
Yeah.
Well, that's not good given that it's due very shortly.
Yeah. I feel like the iteration process is really what's getting to me.
All right, well,
Calculation wise, everything is like kind of makes sense and falls through, but then it's like tuning everything because I feel like sometimes I like tweak something just a little bit and then all of a sudden like it'd be completely off. But yeah, that's just my take.
all right, well, I'm going to try to give you some hints shortly after this, and maybe that will get us in the right direction. What about other people? How are your projects coming?
Everything is too interrelated that like we have one spec that or all of the specs fit except for one and just barely, and we try to fix it and then all the other specs get ruined because of that.
All right, so that's a really good point, and that's exactly what I want to talk about in just a few minutes, is how to deal with this problem, where I have almost all of the specs met, but one, how do I nudge up or down one thing in order to meet the specs? So I will talk about that. How about everybody else? Is anybody done?
Yeah, actually, we done, Professor.
Report written?
We're working on it.
Okay. All right. I mean, I have seen a wide spectrum of responses from Piazza and office hours and talking with the students. And that's why I wanted to try to give everybody as much time as possible, hence the few-day extension that I was able to give. All right, so what I'm going to do in just a few minutes is I will talk about this exact point of how to deal with increasing one spec given margin in some of the other specs. A few announcements before that. Number one, all of those really nice things that you've been thinking about me and wanting to say, but maybe haven't just found the time, CAPE. CAPE is the right place to say all of those great things. CAPE is going to be available, I think, starting today. Until the final exam, it's your chance to give me feedback on this course. I'll say that it's been a challenging quarter in a lot of ways for all of us, one of which is that I don't particularly like lecturing to an empty audience and just staring at my screen giving lectures. I much prefer interacting with you guys, joking with you, and getting your feedback in the sense of, if I'm going too fast or too slow. So, please do fill out CAPE. Give me feedback that can be used to improve the course, things that you liked, things you didn't like. It is important that we do fill out CAPE. It is used. I know that it takes a lot of your time, but I would appreciate if you would fill it out. Second, and most important, how amazing are the TAs? They have been answering questions on Piazza at a pace that I have not seen before. So I'm very hard on the TAs in general. All of my TAs over the past decade will tell you this. The response time is often under 15 minutes. I have never, ever had a class that was under 10 minutes. And these TAs, even right now, with all of the posting that's going on, it's 9 minutes average response time. 9 minutes if it's the middle of the night, 9 minutes if it's 8 a.m. It doesn't matter. The average over the entire quarter is 9 minutes. That is absolutely incredible. You guys really do need to fill out CAPE, if not for me, definitely for the TAs. Give them very high praise. write comments, tell the department how great they are. I personally have nominated both of them for TA awards. You know, I think that they're both incredibly deserving and should be recognized for their effort. But it doesn't just take me, it really relies on you guys telling the department that both Tyler and Abhishek were excellent TAs this entire quarter. So help me out, get them a TA award, and remember to say all those really nice things about me. Do you guys know some good words for excellent or great or wonderful? Any other words?
Fantastic.
Fantastic, all good words.
Amazing.
What are some other ones? Amazing, yeah, these are all good words.
Exuberant.
Perfect. All right, kidding aside, please really do fill out CAVE. It is important to get that done. All right, so there was a couple of questions that the TAs have had, and I wanted to talk about them. One of which was on this test bench. The test bench that I shared with you, that you should have access to, you should be able to put your amplifier in this test bench. If you copied the test bench and it didn't, if this amplifier showed up as blinking, it's because the project name was changed. And so you just need to click on it, click F3 and change the name of the project to match your particular library. But what I want to point out is actually two things. One, the test bench only has an output capacitance of 1 picofarad, whereas the spec in the project is 5. So make sure that in your test bench, you update this to 5. And then second, for the transient measurement, if you want to do the transient with this test bench, what I would strongly advise, you need to replace this source and this source with transient signal sources, so V sine, and put half of the amplitude here, or minus 1/2 here, and plus 1/2 on this side. There have been quite a few questions about how to actually run the transient. That's what you need to do there. Other questions have come up about how to verify that the input common mode range is met. So on our project, we have a spec. Let me flip here for just a second. We have a spec that says the input common mode range is 0.2 to 0.8 volts, and that the output common mode voltage just needs to be within this range of 0.4 to 1.4. So we don't need to actually run any special simulations for the output common mode. Just looking at the DC simulation will tell us whether or not our output common mode is within the spec. The input common mode, the way that you would do this is what we were describing previously when I talked about the test bench. And that is that if I wanted to simulate, the input common mode range, what I need to do is I need to sweep the DC input common mode while looking at the gain, okay? And so back on this test bench here, that essentially means that we would sweep this voltage while leaving these to measure the common mode. And so it's like you're doing a Bode plot, but you're sweeping the input voltage. And we're looking for the points at where it starts to fall off, okay? You know, the exact point of where we'll define the input common mode range, it depends a little bit on the application and how much gain you're willing to throw away. I would simply annotate this and show that across the 0.2 to 0.8 volts, you have greater than 70 dB of gain. Any questions about how to do this part?
Is it okay if like we don't annotate it, because on the graph you could see that it's clearly above 70 dB for that whole range?
Sure.
Okay, cool. Thank you.
I will say that annotating on the plots is generally helpful. You know, Cadence does not produce the best looking plots. It can be very helpful for the TAs and also for yourself to just annotate and show a few things. And annotating is nothing more than putting a little bit of text on or drawing an arrow or a line on top of it. Nothing fancy.
What is this V out that you labeled? Is that something we have to add to the test bench or?
You're talking about, sorry, this part. Is that what you're asking?
Yeah, or in the next one, other one. Because in the setup you have V out is equal to some voltage.
Here?
Yeah.
Yeah, so you don't have to do this. What I was doing in this particular test bench is, in addition to changing the input common mode voltage, I was also showing you how you could verify the output common mode range. And in that case, you have to set the DC operating point of the output common mode. And you do that with this kind of technique where we have this special switch here. And that's what V out was in the previous slide.
Okay, I see.
You don't need to worry about that.
Okay, thank you.
Mm-hmm. Other questions about simulation-based or simulation-related questions?
Yeah, one more thing. So with the TAs, like they basically showed me how to verify the output common mode range. Is that fine to include that graph as well, or should I not include it?
You're welcome to include it. Keep in mind that you have to follow the project pages exactly. And so it's going to come at a cost of something else in your actual write-up. If you think that it's worthwhile to include, that's great. Or if you just want to put it in the appendix, that's also fine too.
Okay, cool. Thank you.
The appendices, I should mention that we will not look at them. We will not grade them. However, you know, these reports can be quite useful in your hands to get internships and to show potential employers. And so I do want to leave open the option to put things in the appendice for that reason. Any other questions about simulation-based stuff? One other suggestion that one of the TAs he gave to somebody, I believe on Piazza, was to overlay 3 different Bode plots rather than have this separate Bode plot that showed kind of gain and phase and the output common mode. You could also do 3 Bode plots where you had the gain at 0.2, somewhere in the middle, like 0.6, and also 0.8, and showed that we met specs across all 3. Either way is fine with me. All right, so now let's talk a little bit about the project write-up. So the project report, a couple of things. One, you need to follow this structure exactly. So page 0 should have this and only this. Page 1, you should outline your design. How did you approach the problem? What are your key design choices? This is really for you to explain your methodology. What we're looking for here is that you came across the design in a logical way. You know, this is maybe not the way that we first started out looking at the design or thinking about the design, but when you eventually got it to work, how would you approach this problem in the future and explain to somebody that you approached this? What were some of the key design choices that you made? Why did you make them? How did you simplify this problem? How did you not end up with just paralysis from 40 different design variables that you had to choose from? Pages 2 and 3, this is where you're going to show us schematics that annotate on the operating point. And so there's a note on Canvas about how to change the default parameters that are shown. Many people have asked this, can you show things like overdrive voltage and current? The answer is yes. It's on Canvas. It shows you how to put basically whatever you want up there. Pages 4 through 7. This is where you are going to show us calculations. Not every single calculation that you did. I want to see the key calculations. And again, this is going towards this idea of how did you get to your end design? And so you're going to show us hand calculations, and you're going to have a table that shows your final SPICE simulated values. So for example, if you set the current through the folded cascode stage to 100 microamps, and your final spice was 95 because you had enough bandwidth that you could turn down the current, put it in the table, discrepancies that are, call it, within 10%, you don't need to explain anything. It's fine. Things that are more than 10% off, I want to understand why. Why are they more than 10% off? And one reasonable explanation might be that you didn't account for precise values of lambda, that you used a rough estimate of lambda and it turned out that lambda was wildly different. I think that's reasonable to put in here. But again, you want to make sure that this is justified and that somebody that was not you or your partner reading your report understands how you got to the final values. If you did optimization and you were able to kind of do hand calculations to show feasibility and then optimized your design in MATLAB, Excel, MathCAD, whatever, what I would recommend doing here is including 3 columns in the table. Your hand calculation, spice from your hand calculation, and then your optimized ones with the optimized spice. And then you can kind of compare all of these such that it's, again, clear how you got to your end result. What I don't want is for you to do hand calculations, come up with numbers, and then say, oh yeah, we optimized it and spice has completely different numbers, but just trust us, it works. That's not guiding the audience or the reader to how you got to these values. We're looking very clearly at your methodology. How did you end up at your final design? One thing that you should, of course, include is your power dissipation. This has to be in your table along with a lot of the other key parameters that you want to compare, i.e. currents, transconductances, poles, zeros. Those should all be in the table, both the calculation and the simulated values. Again, here in the report, there have been a couple of questions about the grading, specifically about this part, 50%. This 50% is not just for optimization strategy. The 50% is a lot from these, design flow, insight. How did you get to this final design? This is really, the meat of your presentation or your report. These pages, that's how you show us and guide us and tell us what you did. It's these that just kind of prove that you were able to do it and that it works. But your opportunity for a lot of these points comes in a very few number of pages. So be very clear here, concise. Again, I don't need to see every single calculation. I want you to tell me what the key calculations are and how you approached this design. Before I go further, are there any questions about this?
Yes. So I talked with the TAs about this because my first hand calculations are like 150% off from what my final results were. And I asked if that's okay as long as I explain what my process was to get to the final values. And so what I also asked about is whether I should include my original hand calculations or if I should work backwards from my final spice values to see what my hand calculations would have been if I knew those values.
So I would recommend putting another column in your table. Mm-hmm. I would do hand, original, and then modified. And then you can just explain why you modified it. For example, you increase the width of the differential pair to get more transconductance. Mm-hmm. Right? Again, 150% is getting up there that it kind of indicates that something else is going on. I would be a little bit uncomfortable with 150% for all of your parameters. If it happens to be one of them and you can explain why, then I think it's okay.
Yeah, that was just a number. It's not 150. It was just a big number outside of 10%.
Okay. Other questions about this part? Okay, so there were a couple of other points that I wanted to make. I often get the question, does this need to be typed? Can they be handwritten equations? Yes, it can be handwritten. It does not have to be typed if you don't want to. Whatever you feel comfortable with, that you can explain this. All right, page 8 and 9, these are simulation results. Here, we're just looking to make sure that your design works. And then page 10, any kind of comments that you would like to leave, issues that you had, things that you learned or maybe didn't learn from the project, as well as I want to give you the opportunity to comment on if you were able to change the architecture, i.e. if your boss wasn't such a jerk and said, use this, but still meet these specs, are there other things that you might have done differently? And if so, what? And this is your opportunity to really kind of think about extending this further. All right, as far as grading, this is not generally, this is the way that we will grade this, based on the write-up, the specs, and the power consumption. Let me show you what we've used in the past as a scoring rubric, just so that we're all on the same page here. We're not going to do this year because we're using GradeScope. Otherwise, I would have shared this with you earlier, but this gets across kind of the general way that we will look at the projects. So again, here, same rubric, design methodology, write-up, specs, power consumption, total. We're going to look at a couple of things. One, what's the flow? Did you understand how to take a multi-stage circuit and describe it in a systematic manner? Did you understand the dependence between the different parameters and how they related to the specs? I would hope so. These are the key equations that we should be deriving. Were you able to justify why the design choices were made, even though there may be some non-critical aspects that were neglected? I.e., we made some assumptions that, were maybe not perfect, but they weren't really critical to the project. Or somewhere in the middle would be that you understood how to design the circuit, you understood how it worked, you could break this up into smaller blocks, you understand the specifications, you might have reached a working architecture, but you made some arbitrary assumptions or maybe even some wrong assumptions along the way, and it caused some difficulties in your design and your flow. Or alternatively, the other end of the spectrum is that you had a lot of difficulty in demonstrating how to design the circuit. You did not describe a logical design flow. There were a lot of arbitrary decisions, and or you resorted to randomly guessing at W over L to the 40th power to try to make this work. Any questions about this part? All right. Analog design, very similar in the sense that, were you able to get equations for the various stages? Do you know how all the blocks work? Can you get all the small signal parameters? Can we find like the DC gain, biasing, that kind of stuff? Whole section here on how to do the biasing, very similar, kind of 10-5-0, knowing how to design the bias circuit properly to not understanding how the current mirrors work or getting the mirror ratios wrong or the constant GM. Frequency planning, obviously understanding that there's multiple poles and zeros, where they are, planning appropriately, using, maybe putting the zero where you want it, positioning it properly. And then lastly, there's some points related to optimization. Was this the first design that worked, or were you able to go back in and improve some of the performance in order to meet various different specs? In terms of the write-up, one, did you follow the format? Is your schematic readable? I know that this can be difficult. Cadence is very bad at making schematics readable. There's a couple of things that you can do that help. One of which is to go into display settings and turn off the grid. This gets rid of the little white dots. You can also use the export or save as image, in which case it saves it as a bitmap, and it'll also invert the colors for you so that you don't have the ugly black background. A couple other things here, just, use the simulation results, and also that you knew how to do the simulation with the test bench. And then lastly, were you able to meet all of the specs? So these are specs from last year. They're different than your specs, but same kind of thing. And then at the end, we're going to give you comments. We will give you positive feedback, the good kind, in the sense of, what did you do well? What did we like about the project? As well as for every project, we'll also give some critiques of things that we think you could improve on, or that would be maybe a better way to approach certain parts of this. And so the TAs and myself, we all contribute to the comments, and we all look at all of the reports. Any questions about project grading, rubric? All right. Then what I'd like to do is I'd like to talk about what one of your colleagues was mentioning earlier, and that's this notion of you're almost there. You are near the finish line. Your design is almost working, but maybe one spec is not quite met. Okay. All right, so let's talk about the various different knobs that we have in this circuit. So for example, what if we are meeting all of the specs, but the gain? So we're a little short on the DC gain. What are the knobs that I have to change that can improve the gain, but more importantly, do not change a whole bunch of the other parameters? Because as one of your colleagues pointed out, yes, there's many ways of changing the gain in the circuit. Not all of them are great choices, because some of them will have dramatic effects on, for example, the phase margin, or on the power dissipation, or a number of other different specs. And so what we want to do here is we want to try to be surgical about things. All right, so what does the gain depend on? The gain depends on GM1 RO1 times GM2 RO2. Okay. This is what gives us GM1. This is what gives us GM2. Okay. This, along with M9, is what gives us RO2. And all of these give us RO1. Okay. All right, so if my gain is a little bit short, help me out. Let's pretend that we have margin in everything else, i.e. we have plenty of phase margin, we have plenty of bandwidth, we're just short on gain. What is the most straightforward way of increasing the gain? Any volunteers?
Increase either GM1 or GM2.
Okay, so we could increase GM1. The problem with increasing GM1 is that what else is going to happen? So our dominant pole formed here is also going to get pushed out. And so if I increase GM1, I will increase the DC gain. It's a reasonably good place, but I have to understand that that's going to increase my unity gain bandwidth and likely decrease my phase margin. So that's one option. I certainly could do that. What else? I could decrease GM2. I mean, increase GM2, right? What does GM2 also change?
The current.
Location
All of
the
these
second
things are
pole.
gonna change the current more than likely.
Location of the second pole.
Yeah. So the second pole is very dependent on GM2. And so the one good thing here is that GM2, increasing GM2 can increase the gain. And I can also push out that non-dominant pole. This, of course, costs me power. What are things that don't necessarily cost me a bunch of power? What are the two things left?
Increase the output impedance.
Yeah. So RO1 and RO2. So these, to first order at least, do not change the gain bandwidth. They don't change the poles. They're more precise in the fact that they affect the DC gain, and they have a secondary impact on some of the poles. Okay. And so if I wanted to pick, I would probably start with RO2 and maybe M9. These two, increasing the length of these transistors can get us a little bit more gain in the second stage. In the first stage, we could increase the length of M4 or M7 in order to increase the gain there. One thing that you should look at very carefully is that recall that at this node, at any of these nodes, it's really it's RO8 in parallel with RO9. And so if I want to increase the total output resistance, I should look at the individual output impedance of M8 and the individual output impedance of M9. If one of them is much lower than the other one, it doesn't do any good to increase the bigger one further. You're going to get diminishing returns here. You're better off increasing the length of the one that is limiting you. And so, I would decrease the one that had the lower output impedance. I would increase its length in order to bump up the output impedance. Especially at the output stage, this is a pretty easy trade-off here. It's a little more difficult at the folded cascode node because of the non-dominant poles that we're going to have here. But it again depends very much on your design. All right, everybody clear on how to do the gain? What if my unity gain bandwidth? What if I'm just short of meeting the unity gain bandwidth? What does the unity gain bandwidth depend on?
GM3 and CC.
So GM1 and CC. Okay. So both of these are very precise ways to go in and increase the unity gain bandwidth. Obviously, playing with CC, if I reduce CC, I can bring in the non-dominant pole and I can hurt the phase margin. And so that may force me to just spend more power in this branch in order to get more GM. What about the, let's see, what other specs here? All right, what about the phase margin? What if I'm meeting all of the specs, but I don't quite have enough phase margin? And let's, for simplicity right now, assume that I'm putting the 0 from this at positive infinity. What are some things that I could do to increase the phase margin?
Is this assuming that you can still change CC? Wouldn't you change CC to adjust phase margin?
Yep. So we can certainly change CC.
And then in turn also change RC so it matches.
So one option that doesn't really cost us power is if I have this 0 currently at positive infinity, maybe I could use this 0 to cancel the pole at the output. So by changing the value of RC, I can cancel out the non-dominant pole, and that's a really easy way to get a bunch more bandwidth without a lot of effort. If I'm already doing pole cancellation, then I have to look, because the non-dominant pole is most likely from this cascode node or this cascode node. And so there, you would actually want to decrease the channel length such that we had lower capacitance at these two nodes. Does that make sense?
Could you repeat that maybe?
So if I'm canceling the pole at the output with RC, so I've set RC to a particular value that cancels the non-dominant pole that would otherwise appear at the output. So that means that the non-dominant pole that's limiting my phase margin is due to either the node here or this node, the cascode nodes. And so if I want to move that pole to higher frequency, that means that I want less capacitance at this node. So what are the things that I could do to reduce the capacitance? Well, one item that I'm not even sure people realized you could do is you could share the source and the drain. So recall back in lecture 5, 6, when we talked about current mirrors, I showed you that you could overlap the source and the drains. And so if I had, for example, two PMOS devices like this, I can tell the simulator that these two are a shared source and drain. The same is true of these two. What does that do? It reduces the capacitance. I cut out one of the CDB or CSB that would be at that node. The other way to reduce this capacitance is obviously to change the device sizes. So I could reduce the channel length and the width proportionally, and I could end up with lower capacitance here in order to push that pole higher in frequency. Do those make sense? All right, now all of these, I will say, they assume that we have margin in other parts of the design. If your design is not meeting phase margin, gain, and bandwidth, these types of tricks of trading one for the other are not going to help you. You have to have all of the specs met, and you're just a little short on, for example, the bandwidth, or just a little short on the phase margin. These are the techniques that we can then go back in and do minor adjustments in order to improve that last little bit. But if you aren't meeting several of these, you have to go back to the drawing board and actually do a lot more design effort. All right, there's one other thing that I wanted to talk about for a minute, and that was how to do the current scaling. So this question has come up a few times. You've designed your amplifier is meeting all of the specs, and now you're doing the bias network, and you want to start ratioing the currents, right? And so just to put numbers to it, let's say that we are dumping 200 microamps here and 50 microamps here, okay? I could, of course, dump 200 microamps in each of these branches, but that may not be the most power efficient method. I would be better off by using ratios and dumping a little bit less power in the bias network. And this is where we have to be a little bit careful, because we have to watch this spec. We have to watch our current mirror M factor being less than 20. So what that says is I can't dump 1 nanoamp in this branch. I have to be kind of within a factor of 20 of this branch, and also still within a ratio of this branch. Okay? And so one method of doing that with the example that I've given here is that, you know, I could dump 10 microamps in this branch, and that would give me a factor here times 20. This and then when I did these, they would be times 5 devices. Okay. Does everybody understand how we're doing this part of it? The next question. Why would I want different currents in this first branch and the second branch of the folded cascode?
Is it because the gains most is in general coming from that first branch, and that's the GM term that you're looking at? So the gain term of the first stage, like the main GM term, comes from GM3. So more current is going to result in more gain.
So the gain of the first stage is GM1 times RO1, okay? Where this is GM1, and the output impedance that we have here is RO1, okay? The output impedance of a transistor is inversely proportional to ID. The GM is proportional to ID. And so already we see this trade-off. I would rather dump current into this transconductance stage here, but at the output, I'm using this load stage to build output impedance, to turn the current back into a voltage. And so there, I actually want less current. And so you will almost always ratio the currents between these two branches. Now, how aggressively you ratio them, it would actually depend on a spec that we haven't talked about, and I didn't give you guys this requirement. It's what's called the slew rate. So if you were to imagine putting in a step input and watching the output settle, the output is going to initially be current starved. And that's when the output is linearly slewing. All of the current is going to drive this capacitance, in this case, CC. So since we don't have a slew rate spec, it's actually in your benefit to run lower current in the output stage and more current in this input stage. And so that's where you would want to do something like a ratio here of, for example, 4:1 or 5:1 or 10:1. And so in your bias circuit, you can ratio these where we would do something like a times 1 device here, and a times 1 device here, and times 20 here, times 5 here, and we would spend 10 microamps, get 200 in this input branch and 50 in the in this load branch. Does that all make sense? Okay. there's one transistor in here or one part of the bias circuit that's a little different and it's a little trickier than the others. Okay. Biasing these is all very straightforward. It follows the exact kind of classical magic battery biasing that we've talked about many times. The trickier ones are these ones. Why are these ones a little bit different? Let's say that we're sending in a current of I1 here, or excuse me, I'm going to call this I2, and I'm sending in I1 here. How much current flows through M6?
I2.
I2.
Yep, I2. How much flows through M7?
I1 plus
I1.
I2.
Uh-huh. So what that means is that the sizing that I showed in the lecture is not quite right for how you should be sizing this structure. You need to account for the fact that this NMOS has more current than the PMOS, or excuse me, than the cascode device. So M7 has more current than M6. So there's a couple of ways of doing this. One, if I1 is equal to I2, then this is actually pretty easy because we will keep the exact same structure, except for M7 will be 2x devices, and this will be a 1x device relative to over here, and we're not changing the bias, everything is fine. It gets more interesting when I1 is not I2, as I was just describing. Maybe we have I1 and I2 is instead equal to I1 divided by 10. Okay. Now, we can't simply use this ratio of putting 2x device here in order to account for twice the current flowing through this, because there really isn't twice the current. There's 11 times the current. Okay. And so you really have to think about how to bias this and do this right. This is the only tricky part in the whole biasing aspect of this.
Yeah, I'm sorry, Professor.
Yeah.
Why is the current through M7 I1 plus I2 instead of half I1 plus I2?
It's half of I1. It's half of I1. I'm taking I1 as being this. I'm taking the total current through here as 2I1. All right, other questions about biasing or how to design the bias network? All right, the only other comment that I'll make is that the constant GM circuit, don't forget about how to properly bias the constant GM. So in particular, in your effort to try to reduce the power, one of the mistakes that students have made in the past is that they overly aggressively try to scale the currents and don't properly size this device. So just go back and remember how the constant GM works when you're sizing this device. All right, any other questions about the project, issues, things that I could help with?
You're still having your office hours Friday, right?
Yep. So I would strongly encourage you, if you're still having issues, post on Piazza, go to the TA or come to my office hours. I really want everybody to get this working. That's my intent in giving you guys a couple of extra days. You know, it does create a lot of work for the TAs to give you these extra days because this cuts into their time of grading. You know, much like you, they're taking other classes, they're doing research, they're also getting ready for finals. And by pushing the project due date later, it's harder on them because the grading gets pushed into when they would be studying for finals. That said, you know, I really felt it was important that everybody gets the project working. And the couple of extra days will ensure that we do get everybody on board and get this working. So use the resources, make sure you spend enough time on your report. You can do this. We're really close. Any other questions about the project? All right, one last comment before we sign off for today then. I did upload, I will upload a sample final. The final format will be extremely similar to the midterm. You'll have a little bit longer, so you won't be as time crunched as the midterm. Format though will be identical as the midterm, just roughly twice as long, not 3 times as long for the final, and it will cover all of the material that we've talked about the entire year. All right, with that, good luck on your project and see you next week. Oh, wait, I forgot one last thing. We will ask a couple of you to present your projects next week. The idea is that I think that you learn a lot in seeing how other students approach the problem. So Monday, we're going to look through the projects very early, first thing, and I will send an email to a handful of students asking you to present. The idea is that you would prepare, I don't know, 5, 6, 7 slides, roughly 10 minutes or less of a presentation. If you want to pre-record it, that's fine. If you want to do it live, that's also fine. But I think that it's very valuable for you to get to see how other students approach the project. I don't always just pick the lowest power projects. You know, we try to pick interesting designs. That said, we definitely will not have these graded at the time. So we have to do kind of a very cursory analysis of this. So if we do ask you to present, please accept and look forward to seeing you guys next week. Thanks. Bye.